continuing our look at probability. So multi-stage experiments where dependents are being repeated. But they're independent events, remember? They're events whose outcome has no effect on any other event. So if I'm tossing coins several times, it doesn't matter what I got the first time, it doesn't affect the second one. Although many people do believe that if you've tossed several heads in a row, they'll go, oh, the next one has to be a tail. That obviously all the events are independent. So if they are independent, then the probability of A, then B, then C, then D would simply be the probability of A times the probability of B times the probability of C, and so on and so on and so on. It's a fairly simple idea. Yahtzee. I don't know if you've ever played Yahtzee. How many people played Yahtzee? You know, only one person out of the whole class has played Yahtzee. Really? Ah, okay, it's a good game. So you roll 5 dice basically, and it's all to do with the numbers that appear on the top of the dice. So they find the probabilities of rolling exactly 4 6s. So you could roll 6, 6, 6, 6, and then not a 6. You could roll a 6, 6, 6, not a 6, then a 6. You could roll a 6, 6, not a 6, 6, 6. You could roll 6, not a 6, 6, 6, 6, 6. And then, of course, you could roll not a 6, then a 6, then a 6, then a 6, then a 6. They're all the different ways we could roll 4 6s. Now, each one of those actually ends up with the same probability. It's just that they're happening in different order. So we get a 6 times a 6 times a 6 times a 6 times 5 6, and so on and so on and so on. It was so long I couldn't fit it all in one line. It all adds up being, they're all 5 on 7 7 7 6, so we end up with 25 on 7 7 7 6 as the probability. Of course, there is an easier way. With independent events, the probability remains the same regardless of the order. We just saw that. It didn't matter where I put the not 6. I got the same probability for each one of those. So I could have simply said, well, it's going to be 5 times the probability of 6, 6, 6, 6, not 6. Because there's 5 different ways I could place that not 6. But the result's going to be the same every time I do it. And then that, of course, is a lot quicker way of getting 25 on 7, 7, 7, 6. That idea becomes quite important in our next topic of permutations, combinations. We'll talk more about that when we start that topic. However, if the events are not independent of each other, then you have to consider the different cases, because it might change the probabilities depending on the order that things occurred. So here's one. 2 letters of the word lotto are randomly arranged. What's the probability we end up with the word two? T-O. Okay. Now, the choice of letters is not equally likely because there's only one L, but there's 2 O's and there's 2 T's. So the probability of an O or a T is going to be greater than the probability of choosing the L. So we can't just say, well, the probability of TO would be, well, T, there's 2 out of 5 T's. That would leave me with 4 letters, and then I'll go 2 out of 4, and that gives me 1/5. That is incorrect. It doesn't work that way. No, we don't do it that way. We have to think of the possibilities. Look at the possibilities. All the different 2-letter words I could have. I could have low. I could have ol. I could have two. I could have ot. I go ooh. I could have tall and lit. Okay? In maths, as far as we're concerned, they're all words. It doesn't matter if they're nonsense words. They're words. So, in fact, the reality is, TO turned out to be 1 in 8, not 1 in 5. Again, that's because each of them are not equally likely. Choosing the O and 2 were not equally likely to choosing the L. All right, so it's just a short little idea today. So 12E, I had a few questions in there to have a go at, and be careful. Maybe some of these you have to consider the cases. Might not be as straightforward.